Oh my goodness.
All right, there we are. Okay, so here we go. Back in the saddle. So yesterday we talked about this whole idea of conservation of mechanical energy. Okay? And as the skier goes down the frictionless incline, normal force is a non-conservative force that is not doing work, so mechanical energy is conserved. And so what we see here is total mechanical energy stay the same, but kinetic energy and potential energy swap places. Okay, good with that? Okay. While it goes across frictionless or friction snow, there's negative work being done that causes mechanical energy to change. Okay. Um, so, does work and energy have direction? Can work and energy be negative? If that's kind of weird to you, can money, does money have direction? It's a scalar. But can it be negative? Can your bank account have a negative balance? That's the problem with America. Okay? We can be in debt. We really like our credit cards. Okay? Correct. Okay? So, I think we looked at this yesterday. So you started with 100 joules of potential energy. You started at rest. Tell your neighbor you got 75 joules of kinetic energy. How much potential energy do you have? And then we're assuming we're at ground zero. So you got 0 here. How much kinetic energy do you have? I went to the bank. Water.
What?
It's water.
I have a nasty penny. Kendall has a black.
I use them for boat projects. There's a nasty penny. All right. So, is everybody good with 25 and 100? Okay. Now, we're going to use these pennies as like an analogy. Okay. Your potential energy is going to represent your savings account. Your kinetic energy is representing your checking account. Your mechanical energy is your overall balance. Doesn't really matter which account it's still yours. Okay. Now, if we do any withdrawals or deposits, that's going to change your overall balance. That's going to change your overall mechanical energy. That's going to represent work done by a non-conservative force. Good with that? Okay. I don't expect you to do this at home. This is just something just to give you something like, oh yeah, think about the pennies. Oh yeah. Okay, that's all this is doing. Okay. We are not going to do energy bar charts this year. We're like, going to move out on the time. Okay, so if you come across something like draw the energy bar charts, go, ha ha ha, don't have to, sucker. Okay. So let's look at the kids sledding on the icy embankment again. Okay, so when we do these problems, when you get to your worksheet, what you're going to be doing is step 1 is you're going to define where your initial and your final positions are. So initial position here, final position at the highest point. Step 2 is you're going to define where ground zero is. The lowest point you care about between your initial and your final is what, like this one, the lowest point we care about between initial and final is the initial. So we're going to make ground zero at this location, at this height. Good with that? The next step is we're going to ask ourselves what type of energies are present at the initial location and at the final location. Okay? So kinetic energy is equal to 1/2 mass times speed squared. So the question we're going to ask ourselves is does it have kinetic energy? Is it moving at that location? That's what we're asking ourselves. Okay. Gravitational potential energy, the equation is mass times 9.8 times height. So we're going to ask ourselves for does it have gravitational potential energy? Is it above ground zero? Okay. So at the initial location, does it have kinetic energy? Tell your neighbor and tell them why or why not. Does it have kinetic energy? Correct answer is thumbs up, yes, thumbs down, no. Kinetic energy at the initial location. It is moving. Yes. So give yourself some pennies in your checking account. How many? Great question. I don't know. I don't know. You pick. Doesn't really matter. Okay. Now, at the initial location, do you have gravitational potential energy? Tell your neighbor why or why not. Correct answer is no. You are at ground zero. Okay? So no pennies for that. No pennies in savings. Okay? Now, your total balance, your total mechanical energy is what? Whatever you have in your kinetic energy. That's your mechanical energy. Again, you don't have to draw these. I'm just trying to give you. Okay? Good with that? Now, you're going to look at the process going from initial to final. And you're asking yourself, is there any work done by non-conservative forces? Is there any work done by non-conservative forces? See if you can think about it first. Any work done by non-conservative forces as it goes from the initial to the final? Have a conversation.
If there was friction, then I think.
Oh. Is there any non-conservative forces doing work? Here's your free body diagram. Gravity, conservative or non-conservative? Conservative. Normal force. Conservative or non-conservative? Uh-oh. But it's not if it's acting, it's if it's doing work. Is normal force doing work on the sledder? Tell your neighbor yes or no, and why or why not. Correct answer is no work done. It's acting perpendicular to direction of motion. There's no part of normal force that is acting parallel to the direction of motion. Okay, so there's no withdraws nor deposits. Okay, mechanical energy is conserved. At the end, figure out which energies are present. Kinetic energy, potential energy, both, neither. At the highest point. Final is at the highest point. So, what do you say? Is there kinetic energy? Is there kinetic energy? No. We're stopped at the highest point. Do we have gravitational potential energy? Yes. So, what we're going to do is we're going to transfer all of our money into savings. Yep. Does that make sense? Okay. What happened to our overall balance? Stayed the same. So, answer that question. Tell your neighbor what the answer is. Is everybody good with C? If you move $20 from your checking to your savings, your checking lost $20, but your saving gained $20. Good? Mechanical energy is conserved. This will always be true if mechanical energy is conserved. It just transfers from one account to the next, but your total amount of money is still in the bank. Okay? All right, so let's change the scenario and say there is friction. Uh-oh. So we're going to run through this again and pick our initial and our final. That really hasn't changed. Okay, we're going to pick ground zero, lowest point we care about. Still there. Initially, do we have kinetic energy? Yep. Still have potential energy? Nope. Our initial conditions have not changed. They're still the same. Here's why. Because friction affects the process from initial to final. Okay? So, was there any work being done by non-conservative forces? Ruh-roh. And was friction doing positive or negative work? Negative. So we're going to withdraw some money. How much? I don't know. You figure it. Yeah, you pick something. Don't take it all. Okay? Good with that? Now, at the end, what type of energies do you have? Tell your neighbor. What type of energies do you have at the end? At the final location? At the highest point. No kinetic, but yes potential. Good with that? Okay. So we took away 2 pennies. So all that's left is what's in potential. Okay, so transfer your funds over after you took a withdrawal out. Okay. How to now answer this question? Talk to your neighbor. Okay. I want to take some time to digest this just a tad bit. Is everybody okay with the fact that kinetic energy is losing? Like we lost kinetic energy. It went from something to nothing. You okay with that? Potential energy went from nothing to something. It gained. So what I'm asking you to do is make a comparison between how much did kinetic energy lose compared to how much potential energy gained. That's what this question is drilling in at. Tell your neighbor what you think and why you think it. Correct answer is okay. The way I did it, I had 4 pennies in kinetic energy. I lost four. I lost four. Excuse me. Lost 4 pennies for kinetic energy. I gained 2 for potential. Kinetic energy lost more than potential energy gained. Hey, how would you say that? If you're like, that was really confusing, what would you say? How would you phrase it? Suggestions. Some people find this phraseology confusing. So I'm just trying to pull the audience here. What would be a better way to say that? Let me know if you have a suggestion. All right. So how does this transpire, like manifest itself in life? The fact that you only have how could you observe this? How could you observe what could you observe about this letter that said, hey, we potential energy gained not as much as potential energy lost? What would be different about this scenario versus the one without friction?
You would have been, well, the sled would have been slowing down before gaining height.
Let's say we start with the same speed. So that would be true if we worried about this part. But let's pretend that the same speed. We just looked at friction going on this part here. But you're on the right. You're thinking the right idea, Caroline.
It takes less time to get to the top.
Great thought. Maybe, probably, but a limitation with working energy is it doesn't answer a time question. The kid ends up not going as high. You okay with that? Like, I'm just trying to make a connection, and like, you got some energies. How does that play out in life? Okay, good with that? Sure. All right. So here's a real question, like something you get on your homework. All right. So step one. We're going to pick our initial and our final location. So we are throwing a rock off of, at 25 meters a second at 30 degrees off of a 10-meter high cliff. How fast is it going when it hits the ground? Okay. So initial is up the top, final is at the bottom. Step two, where are we going to define ground zero? Lowest point between initial and final. This one's kind of screaming obvious, at the ground. Okay, so ground zero is at the ground. Okay. Step three, we're going to ask ourselves what energies are present. Do you remember this slide, how we camped out on this yesterday? Kind of said we're going to use this a lot. Or here we are. So we've got kinetic energy initial plus potential energy initial plus the work done by non-exertive force equals kinetic energy final plus potential energy final. And we're going to ask ourselves what energies are present at the initial and the final locations. Okay. Initially, tell your neighbor if we have kinetic energy or not. Initially. Tell them why or why not. What do you say? Yes or no? Kinetic energy initially. This is after it leaves your hand. It is moving 25 meters a second at 30 degrees. Yes, there is kinetic energy. Tell your neighbor, is there gravitational potential energy initially? Tell them why or why not. Yes, there is gravitational potential energy. You are above ground zero at the initial location. Okay? Now, from the process from initial to final, is there any work done by non-conservative forces after it leaves your hand, right before it hits the ground? Tell your neighbor. Is there any work done by non-conservative forces? Correct answer is, what forces are acting on it? Just gravity. That's a conservative force. So, no work is being done by our non-conservative forces. So, we can get rid of this. This goes to zero. Okay? No work done. Tell your neighbor you have kinetic energy at the final location and potential energy at the final location. Tell your neighbor. At the final location, what energies are present? What do you say? Do you have kinetic energy? If I dropped a bowling ball on your foot, would it hurt? Yes. Why? It's moving when it hits your foot. Okay? So, yes, you have kinetic energy. Do you have gravitational potential energy? No, you're at ground zero. Your height is essentially so close to zero, we're calling it zero. So, this is your original setup. Good with that? Now, once you have eliminated which energies are not present, then what we're just going to do is this. We're going to substitute kinetic energy is equal to 1/2 mass times speed squared initial. Potential energy is equal to mass times 9.8 times height initial plus zero. You don't have to do the plus zero if you don't want to. I would not. I'm just trying to teach. Okay? Kinetic energy is equal to 1/2 mass times speed squared final plus zero. Again, don't put the plus zero. I'm just trying to be explicit. Okay? Now, at this does everybody see how I did that? Why I did what I did? Mathematically, can I simplify anything at this juncture? Do you see a mass in every single equation? Expression, not equation. Yes. So if we divide by mass on both sides, we can eliminate mass. What do you think that means in real life? Like, how does that demonstrated in real life? Does that mean the rock's massless? Just like poof. Okay. It doesn't matter how massive it is. Okay. It could be half of a kilogram. It could be 500 kilograms. The answer to this is independent of the mass. You okay with that? Okay. So once you have that, now we can just plug in numbers. So we have 1/2 times the initial speed, 25 meters per second squared, plus 9.8 newtons per kilogram times height, 10 meters, is equal to 1/2 times final speed squared. Really? That's it? Is anybody else like feeling like that seemed too easy? Like what do we not take into account? Say it a little louder. Okay, we are ignoring air resistance. We're going to continue ignoring air resistance. There's something up there that should be like 30 degrees. What? Ah, vector at an angle. Like, right? Does energy have direction? No. It does not matter what the angle is. That's a direction. What? First time ever in physics. Don't worry about it. Okay? The other thing that some people have issues with is like, hey, isn't it going up and then coming back down? Yep, sure is. All I care about is my initial and my final. I don't really care how it got there. Okay? So, that's it. You just do the math. So 625, 312.5 plus 98 equals 1/2 v squared. That's 410.5. Then you have 821 v squared. Take the square root, and that was 28.65 meters a second. Think. Good with that. In the realm of reality, it's faster than 25. Not going the speed of light. Call it good. Good with that? Okay. See the process I went through. Any questions? All right. Oh, hold on a second. Let me throw this up. Okay, let's do some penny manipulative here. Okay, initially you had kinetic energy. Give yourself a couple pennies. I don't care. Potential energy. Oh, sorry. No, you don't have to write this down. You're just doing pennies here. Potential energy. Give yourself some. What happened? So take your initial balance. Like, what was your initial balance? Total mechanical energy. All right. Then it goes through this process off the cliff. What happens? How are you transferring your money? Okay. How did the change in potential compare to the change in kinetic? Not the final, but the change. Okay. If you deposited, if I gave you 20, if secretly, Secret Santa, I deposited $20 in your checking account, will I know your balance? No. Would I know your change in your balance?
Yes.
Yeah. What would the change in your balance be? Plus 20. Does that make sense? The difference? Which one, how does the change in potential compare to the change in kinetic for this scenario? We took this whole stack of pennies in our savings account and we transferred it into our kinetic, into our checking account. In this example, I took 5 pennies out of my savings and deposited or transferred it into my checking. So I lost 5 pennies potential, gained 5 pennies kinetic. Good with that? Okay. All right. Give this one a shot. I'll give you a couple minutes. Yeah, you do the equation stuff. I want you to do the equation stuff. I don't really care about the pennies at the moment. Pick your initial, pick and final, pick ground zero. Figure out what energies you have. Okay, initial, final. Where am I going to make ground zero? The lowest point that I care about between the initial and the final, which would be here. Everybody good with that? Now, there's nothing illegal with saying that the ground itself is ground zero, but sometimes you're not given all that information. Okay, so I'm going to coach you to make the lowest point, or make ground zero the lowest point between your initial and your final. Did it go below that? Sure did, but do you care? Nope. Okay, so initially, do you have kinetic energy? Thumbs up, thumbs down. Kinetic energy initial. Yes, you're moving 1 meter a second. Potential energy, initial. Thumbs up, thumbs down. Yes, you're above ground zero. Was there any work done by non-conservative forces? Yes, straight up. Just told you. Okay. Was there any kinetic energy final? We're assuming so. It's asking for how fast. I sure hope so, because if that'd sting, like, okay. Gravitational potential energy final. If we made ground zero at this point, then no. Okay. So you have 1/2 mass times speed squared plus mgh. Is this work being done positive or negative? Work. Negative. Okay, first question I want to ask. Can masses cancel out? Can I cancel out mass? Oh, why not? I've got mass on the left side and on the right side. I don't have mass in every expression. I need a mass here. Don't have it. Can't cancel out mass. Okay. Now, the other thing I want to hit, what is the value of height for h? It is the distance above ground zero. This is 5 meters. Good with that? Questions there? So when you do it, this is negative 3,000 joules. You got 500 kilograms times 9.8. 1/2 500 times 1 squared plus minus 2,000 equals 500 times. As you solve for that, you should get 9.3 meters a second. Okay, so that's what your worksheet's going to look like. Okay.